Hello everyone. Today we are going to solve an attractive problem on coloring. So here you go with the problem, and it states that you have a 2D plane, and on this 2D plane there are infinitely many points. Each of these points are colored with red or blue, one of these colors. And we have to prove that one of these colors have the property that there exist 2 points of that color at any given positive real number distance. For example, if you give me pi, which is a positive real number, there exist 2 points of that color whose distance is pi. We are going to solve this in an ingenious way, and let's go into the solution. We also have an attractive problem at the end that is a generalization of this problem. So stay tuned till the end. So here is the 2D plane that we are going to consider, and all the points of this plane are marked with red and blue colors. We have to prove that one of these 2 colors have the property that there exist 2 points at any given positive real number distance. So let's prove it by considering first any one point. Maybe it is in blue color or red color. Maybe let's say I start with a red colored point. Draw concentric circles, or just consider concentric circles around this point. Concentric circles are the circles obtained with the considered point as its center. So consider all possible concentric circles with every possible radius. Now call a circle monochromatic if all colors of that circle is the same. For example, if the entire circle is colored with blue points, or if it consists of only blue points, then we call it as monochromatic circle. There is a beautiful property of this circle. If you have a monochromatic circle, then one can say that there exist 2 points that can represent distance all the way from 0 to the diameter of the circle. The idea behind this logic is the following. Consider all possible chords that emanate from a particular point, or that starts from a particular point and reaches every point along a semicircle, and this would give us distances ranging from 0 to the diameter of this circle. And since this process is continuous, every possible distance from 0 to diameter is possible. And now, if you consider monochromatic circles out of these concentric circles, then we have 2 possible cases. Let's say case 1 is infinitely many monochromatic circles. If there are infinitely many, then it is true that one of these 2 colors, red or blue, constitutes infinitely many of these monochromatic circles. Because we have only 2 colors, and if they are occurring infinitely many times, one of them must occur infinitely many times. Let's say blue colored monochromatic circle occurs infinitely many times. Now this would imply that blue color has the ability to represent any positive real distance. By the word blue color, I mean 2 points of blue color. This is because of the property we just saw previously. Because the diameter goes to infinite. There are infinitely many such circles, and we know that these infinitely many circles should also be considered goes to unbounded radius. That is, you cannot bound the radius of this monochromatic circle. If that is the case, then one of these 2 colors, blue or red, must go unbounded. And since it is growing unboundedly, we may represent any given real number distance between that color. And hence, we have proved the question for this case. Let's go to case 2. Now, case 2 corresponds to finitely or infinitely many monochromatic circles, but they must be confined by some radius. So this corresponds to monochromatic. Again, even here we can have infinitely many circles, monochromatic circles having bounded radius. Let's say the bound is capital S. So within the distance of capital S, all the monochromatic circles are confined. So let's think about the points outside the monochromatic circles, and that means of radius more than S. So let's draw circles around this circle of radius S. Now clearly these are not monochromatic. These circles are not going to be monochromatic. And there are now two possible cases. Either the last monochromatic circle whose radius is S has red colored points or blue colored points. Let's take the subcase 1 as red monochromatic circle being the last concentric circle, and hence we see that all possible distances from 0 to diameter of this circle is feasible with these red points. And when you go to distances beyond this diameter, we know that all the outer circles are non-monochromatic, hence they contain both of these colors. Both red and blue must be present. So one can choose the red color and join it to the center. Now this distance can accommodate all possible distances more than the diameter. Hence, one may conclude that it is possible for subcase 1. But coming to subcase 2, when last monochromatic circle is blue. Let's consider this as blue with radius S. And now, I claim that blue is the color asked in the question that satisfies the condition given in the question. Why so? First of all, this blue color can accommodate all distances from 0 to its diameter d. And when it comes to distances more than the diameter of this circle, then we have to consider a point which is at that distance from this circle. Let's consider the distance to be some k. Then take the circle of radius k plus s. And clearly this circle is non-monochromatic and hence it must have a blue point on it. And let's say that this is a blue point. So from this point, draw a circle of radius k, and it must be tangential to the blue monochromatic circle, and hence it must intersect at a point. So this point must also be blue because the original monochromatic circle was assumed to be blue in the subcase 2. So hence the distances between these 2 points is k, because this is S and this has to be k. So hence any possible such distance can be now achieved by this logic. And if the monochromatic circle do not exist as such but they tend towards the radius S, you can do a similar logic and you can take the distance from the red center to be not k plus s but little lesser than k plus s. Any arbitrary value closer to k plus s would work, will intersect the blue monochromatic circle. And this is how we can prove the existence of a color that can represent distance between 2 points for any given positive real number. So I hope you enjoyed this view of geometric combinatorics. So there is a generalization of this in 3D, and here you go with that question. So now we have 3 colors in our hand, red, green and blue, and all points of the 3D space is colored with these 3. Now we have to prove that one of the colors attain all possible distance, which means that it can represent any positive real number distance for 2 points of this color. So think about this and comment your ideas of this problem. Let's meet in the next video. Happy learning. Bye.